Hello, chemistry students. Welcome to lesson 1 for the week of April 6th. Today we are going to learn about the ideal gas law. So the ideal gas law has a couple of things we need to consider. Gases are only considered ideal, which means this equation only works when the following conditions are met. So at a certain 1 atm of pressure and 273 of Kelvin, at ideal conditions, the volume of an ideal gas will be this 22.4 liters. Okay, so particles take up a volume of 22.4 liters at STP. That means standard temperature and pressure. And then number 3, particles have 0 intermolecular interactions. So we kind of pretend that ideally these gases aren't ever crashing into each other, they're not repelling each other, they're not attracting each other. And so that's just kind of a set of assumptions we make. You don't need to worry about being tested or quizzed over those, because, and that's what this slide's going to show you, really, our real gases have volume. In the ideal gas law, it kind of ignores the fact that the molecule itself has volume. An ideal gas assumes that the molecules don't ever interact, but really, there will be some kind of intermolecular forces and some collisions between gas molecules. So that's just kind of our definitions of how this works. Now this is where you're going to need to know stuff for our homework today. So the ideal gas law contains all of the variables that we've been talking about so far this unit. So the equation for the ideal gas law is PV equals nRT. Sometimes it's called PIV-NRT, okay? But it's pressure times volume equals N, which is the amount of gas, times R, which we call the ideal gas constant, and then T is temperature in Kelvin. This value for the ideal gas constant, 0.0821, is on the back of your class periodic table, that yellow periodic table. That constant has these really kind of strange units, atmospheres times liter divided by moles times Kelvin. So it has those weird units, which is why our other values have to be in those same units, okay? And they always will be given to you that way for our class. So I want to show you this before I show you my next little demonstration. Remember, box in your givens, circle your unknowns. It will help you pick the equation, and then we can substitute and solve. Okay. So before I go to my document camera, I want to take you to this Phet Simulation. And I have my email pulled up. That was weird. Okay, here we go. So this is from the University of Colorado. This will be up on the DIY extra credit labs for y'all to take a look at here soon. But this is going to show you an animation of how those 4 variables interact. So I'm going to click on the ideal gas property demonstration. And you see I have a lot of stuff that I can manipulate here. And it ends up kind of being fun to play with. But I'm going to increase the moles of gas, the amount of gas, by pumping in some air. And I can even pick a smaller molecule if I like, and add some more of that gas, and then some more of the heavier gas, okay? So the variable I just manipulated was N, the amount of gas. I increased the amount of gas. And you'll see that that affects the pressure as well. So over here on the right-hand side, I have that nothing is being held constant right now. So if I increase the heat, according to kinetic molecular theory, as it gets hotter, you see that those molecules start moving faster, especially the smaller red ones. They can heat up much faster. Okay, so you'll notice as I do that, not only is my temperature increasing right here, but over here my pressure reading is also increasing. So I'll pump up some more heat, and you can see that that's changing the pressure. Now I can also change the volume. So I'm going to let y'all see if I increase the volume, we see a decrease in pressure. Well, watch what happens to temperature just when I affect the volume. Okay. So we're noticing that we have all kinds of things interacting. All right, I'm going to reset it and add in some more different types of air. Get some more blue guys in there too. And I'm going to do it so that pressure is constant. Okay? So if pressure is constant and I increase the heat, when temperature goes up, volume goes up. Okay? It's a direct relationship. When temperature goes down, volume goes down. It's a direct relationship. And that's, remember, Charles watches direct TV. I can also do this where I hold temperature constant. Okay? So if temperature is constant and I'm changing the volume, okay, when volume goes up, we can see how that affects pressure. When I decrease volume, okay, we're able to kind of affect the temperature in that way. All right, check that DIY lab for that on your teacher's Canvas page. You can get some extra credit for filling out the little report if you want to get looking at that. But let's look at some of our calculations. Okay, so we just have 3 little practice problems to take a look at, and I've already boxed and circled. So for sample problem 1, how many moles of N2? So I circled that as my unknown, are required to fill a small room with a volume of 27,000 liters to 0.985 atm at 298 Kelvin. So I'm going to come through and, using my units, label what those givens are. Okay, so moles in my, let me go like this, PV equals nRT. Moles gets the letter N. So I'm solving for N. L, liters, is the unit for volume. Ooh, and I have these ones written backwards up here, I just noticed. That was silly. I took bad notes. There we go. So liters tells me this is my volume value. ATM makes this my pressure. And K makes this my temperature. Okay. So when we're picking which equation to use, which gas law, only one of the gas laws that we've talked about has moles in it. And it would be this one, moles. So as soon as I see moles, I know I'm going to be using this equation. Now the only thing they didn't give me in this question, if you look, I've got PV, N, but I don't have R in this question. Because R is not a variable, it's a constant. Which means I have to look back here for it. On the back of your periodic table, the ideal gas constant, 0.0821. So even though they didn't give me that in the problem, I'm going to write it down just so I don't forget, equals 0.0821. Let's look at how we're going to solve this then. So I found my givens, my unknown, and I've picked my equation. And I'm going to see if I can get all of this on the screen at the same time. Maybe. Okay. So I wrote in a different color, PV equals N, because that's what I'm solving for, times R times T. So let's substitute. For pressure, I'm going to use my atmosphere value. So we're going to say 0.985. I'm plugging that in as P. Check. For volume, I'm going to use my liters value. So times 27,000 equals, so I did my volume. For N, I don't know what it is. So when we don't know what it is, we usually use X. Okay. So I substituted for N. For R, we always substitute 0.0821 is our constant. Check. For temperature, I need my Kelvin value, so 298. Check. So we end up with that. This times this equals X times that times that. Doing our algebra. Some of you are automatic at this, no problem. Great. You can pause me, try the work on your own, and then check it. If you want to walk through it with me, you still probably want to pause to do your own work as we go. But let me show you what I have. Okay. So I have that same thing. The first thing we want to do in algebra is combine like terms. So on the left-hand side of the equation, I have 2 numbers. They're like terms, and I can multiply them. On the right-hand side of the equation, x as a variable is not a like term, but I can multiply these 2 numbers. Okay? So plugging those into your calculator, you're going to end up with 26,595. That's this answer times this answer. So that equals x times 24.4658. Okay, and I'll show you where I got that number from. That's just this one, 0.0821 times 298. Okay, So I just combined like terms. Right. So now I have x being multiplied by a value. Mathematically, to get rid of times x, we need to divide by it. So I'm going to divide both sides by this so that I can have it cancel out. So now on the right-hand side of the equation, I have x equals this top number divided by the bottom number. And it's been a handful of students in each class. I've noticed you're dividing it backwards, okay? So remember, it's always the top divided by the bottom. And if we plug that into our calculator, okay, so 26,595 divided by 24.4658, okay? You can't see my calculator, can you? There we go, 1,087.02. All right, so I'm going to write that down, 1,087.02. Now be careful on the homework. Some students have been emailing me saying that their answers aren't correct. If they ask you to round to the nearest whole number, that would be your answer. To the nearest tenth, that would be your answer. So just be careful on the rounding, but that's how we do the math. Now, I don't like doing algebra with numbers. This looks messy to me, okay? I like doing my algebra before I plug in anything, and I'll show you what that looks like. Some of you might like this, some of you might not. It's up to you, okay? So if I know I want n by itself, then I'm going to just get n by itself before I substitute in numbers. So right now I have n times r, so I'd say divided by r would get rid of it. N times t, so divided by t would get rid of it. And then I do that same thing to the other side of the equation. So it's going to be divided by rt, which means before I even used numbers for this, PV RT, and I can plug it in saying x equals this answer times this answer divided by this one times this one, which is what my algebra did. It was just a little bit easier if you do it this way, I think, but you can do it either. I'm not telling you which one you have to do. Okay, let's take a look at number 2. Dinitrogen monoxide, N2O, is laughing gas, and it's used by dentists as an anesthetic. So I see a number. Here's a given. I'm going to box it. 2.86 moles, which I know gets the letter N in my equation, of a gas occupies a 20-liter tank. Liters means volume. At 296 Kelvin. Kelvin is a temperature. What pressure in the tank, or is the tank in the dentist's office, it should say. So my givens, my unknowns, helps me pick my equation. I need 1P, 1V, 1N, and 1T. And where's R? Oh, way down here. Okay, the ideal gas constant. So I'm going to include that R equals 0.0821. All right. So I'm going to do the algebra before I plug in numbers, just so y'all can see that real quick. Okay. PV equals nRT. I'm solving for pressure. So that means in order to get pressure by itself, right now it's pressure times volume. So I need to go pressure divided by volume, so that I just have pressure equals whatever I did on this side divided by volume. So I've got N times R times T on top, not answer, divided by volume. That's going to get me pressure. Now, if you don't like that because it's different, that's fine. You don't have to like it. Let me show you the other way as well, okay? So I'm going to plug in my values, and I'm covering it up so I can't quite see it just yet. There we go. So the pressure they gave us is X, right? We don't know what pressure is, but they told us that that dentist has a 20-liter tank. So I plug that in as volume, equals moles, and they told us in the question that it's 2.86 moles times R, and R is always 0.0821 times temperature, which is my Kelvin number of 296. Okay, there we go. It's written a little more neatly that way. Please pause it and do the algebra yourself if you can. For real, you can do it. Okay. Thank you for pausing and trying it on your own. what I have on the right side of the equation, I can combine three like terms. So I can take 2.86 times this times this. Okay, so I'm going to put that right here in my calculator. 2.86 times 0.0821 times 296 gets me on the right hand side of the equation 69.502. Okay. So I'm going to go ahead and say I didn't have any like terms to combine over here, so I still have x times 20 equals this answer, 69.50. X is being multiplied by 20, so I do the opposite, which is I divide both sides by 20, so that this cancels out. I have x by itself equals this answer on the right. So the top number, 69.50, divided by the bottom number, 20. 3 point, and you can't see that, there we go, 3.475. Okay, 3.475. And that would be ATM. Okay, that's how we solve it. Okay, you'll notice what I did over here, N times R times T divided by volume 20. You'll get the same answer that way. Okay, last one to look at with you. Same process, different problem. They're asking you to calculate volume. So I'm going to circle volume is my unknown. Calculate the volume, which, here's a number in unit, here's a number in unit, here's a number in unit. Okay, so moles, we put in as N. If you can't remember, y'all, it's back here on your periodic table. You can print one of these off of Canvas. It's on each module. Okay, but it tells you after the equal sign is moles, and after the equal sign is N. Okay, doesn't like that color, I don't think. All right, ATM is pressure, and K, Kelvin, is temperature. Okay, where's R? R is always 0.0821. So for my equation, PV equals nRT. So I'm going to plug in the different color. Let me switch. 1 for my pressure times volume, which I don't know, so we'll plug in X for that, equals nRT. So I've got 3.74 times my ideal gas constant times the temperature they gave me, 273. Okay, so pause it, please. Solve it on your own. Let's see how we do. I'm going to do it on my own too. Let's see. Okay. So what I just did was combine like terms. Moles times constant times temperature. And I got 83.825. So I combined like terms, and I got 83.825. And on this side, I still have 1 times x. Well, I should divide both sides by 1, right? And I get still 83.825 as my answer. That would be the volume of this gas. Please remember that Miss O'Brien has been making homework tutorials. If you're struggling on your homework, or if you get a lower grade on your homework quiz than you're expecting, take a look at Canvas or the YouTube channel, and you can watch her do usually just the odd problems to help you out. This is kind of the last math we're going to do for the week. Our next assignment won't have the same kind of calculations. So if you've been struggling with that, there is light at the end of that tunnel. Thank you so much, y'all. I hope you're doing well.